I'm Ethan. I'm just up the road at Stanford, finishing up my PhD next month, which is very exciting. And I'm really excited to tell you about this work that I've been doing over the last few years using ultra-faint dwarf galaxies as laboratories to study dark matter. So I wanted to start here on my title slide. So this shows the beautiful Blanco telescope in Cerro Tololo, Chile. Very clear, beautiful night sky. And as I'm sure you've all experienced, if you look up at the night sky on a clear night, you can see the disk of our own Milky Way galaxy very clearly. And the Milky Way has about 60 billion suns worth of mass in stars. And that actually makes it a pretty typical galaxy on a cosmic scale. There are many galaxies in the universe that are more massive than the Milky Way, but there are also many galaxies that are less massive than the Milky Way. And in fact, if you're in the southern hemisphere looking up at one of these clear night skies, you can see two of these galaxies by eye. And these are the large and small Magellanic Clouds, which are actually visible in this image. And these respectively have about 3 billion and 1 billion suns worth of mass in stars. So this makes them about a tenth and a hundredth as massive as the Milky Way, respectively. So these two galaxies have actually been known about for a very long time. They've been recorded basically throughout the course of human history by indigenous people in the Southern Hemisphere. The first documented recording that we still retain of these galaxies comes in the Book of Fixed Stars. This is by a Persian astronomer written in 964 AD. And of course, these galaxies were documented pretty copiously by other astronomers throughout history, of course, famously by Ferdinand Magellan in the 1500s, although the name Magellanic Clouds was only given to them much later. So just to give you a sense of how the discovery of these small dwarf galaxies has gone over time, I like to show this plot. So what this shows is the cumulative number of these faint dwarf galaxies that we have detected around the Milky Way as a function of time. So the line here starts out at two galaxies, the large and small Magellanic Clouds, because we've actually known about those forever since antiquity. And then in the 1900s, something different happened, and in particular, a number of so-called classical dwarf galaxies were discovered orbiting the Milky Way. So these were actually found by visually inspecting photographic plates, and I wanted to kind of walk you through how that goes, just to give you a sense of these discoveries. So this is a rendition of a photographic plate on which one of those classical dwarf galaxies named Sculptor was discovered. So it turns out that Sculptor only has about 4 million suns worth of stars in mass, making it even a factor of 100 smaller than the small Magellanic Cloud. So this is really a very tiny galaxy. But we know, based on the kind of clumpiness of the stars in this field and the motions of these stars, that Sculptor is, like the Magellanic Clouds, relatively nearby. It's at about twice the distance of the large and small Magellanic Clouds, roughly 100 kiloparsecs, so a few 100,000 light years. And this was actually discovered by Shapley, who was inspecting these photographic plates. And what he wrote at the time of discovering this galaxy was that it appeared to be unlike any known stellar organization at the time, of course, and that the finding of a similar system named Fornax, which is another one of these classical satellites, suggested that a description of these objects may be of general interest, which, as we'll see, is really quite prescient. So around the year 2000, something really amazing happened with the discovery of these faint dwarf galaxies. And in particular, what happened was the survey known as the Sloan Digital Sky Survey, or SDSS, brought digital imaging over a large region of the Northern Hemisphere that essentially automated the search for these very tiny galaxies near the Milky Way. And this resulted in the discovery of another 16 dwarf galaxies, so bringing the total, including the classical satellites and the Magellanic Clouds, bringing the total number of dwarf galaxies known around the Milky Way up to 27 by the year roughly 2010. So I want to give you a sense of how it is that Sloan was able to discover many more galaxies, and to give you a sense of their nature as well. So this image actually contains one of the dwarf galaxies that Sloan discovered. But unlike in the case of the sculptor dwarf galaxy that I showed you on the previous slide, you should not be able to see the dwarf galaxy in this image by eye. If you can, please let me know, and we can do we can write lots of really cool papers. So let me help you out here by highlighting the stars that happen to belong to this galaxy. So this galaxy is named Segue 1, and it's incredibly tiny. It only has 300 suns worth of mass, right? So even much less massive than the sculptor galaxy that I showed you before. And in fact, Segue 1 is the darkest known galaxy in the universe. It has the fewest stars worth of mass of any galaxy that we know of. So I should say that the green stars that I'm highlighting here are actually confirmed to be members of this dwarf galaxy. And I'm going to walk you through how that's done. This is essentially using spectroscopic measurements to determine the motions of these stars and infer that these circled objects are part of the same gravitationally bound group. And just as a kind of teaser for the second part of the talk, it turns out that the motion of these stars is much, much faster than what you'd infer from the visible matter alone, which means, another way of saying that is that there's a lot of dark matter in this galaxy. In fact, Segue 1 and other ultra-faint dwarf galaxies are the most dark matter dominated objects that we know about in the universe. So let me walk you through how we find a galaxy like Segue 1, because it seems like magic based on the two slides I just showed you. So the idea is to start, we have a stellar field observed by some survey like Sloan. And in general, it's not obvious where a very faint galaxy might live in this field. I see the question in the chat, and I'll come back to it. It's a good one. So in general, it's not obvious where a faint galaxy might be in a stellar field like this. Luckily, what we know is that stars in these dwarf galaxies are generally very old, and they occupy a certain region of this space of luminosity versus color that depends on their distance. So essentially what we can do is use this shape as a template and scan over many possible distances that a group of stars might occupy until we find a distance where a clump of stars appears. And that's exactly what happened in the middle panel here. This is the distance at which a clump of stars is most likely, right, to occupy the same distance. And you can start to see a little bit of a clump in the lower right hand part of the middle image. And then, of course, we can characterize the significance of that clump using some kind of spatial kernel. And if the clump is significant enough, then we call that a candidate dwarf galaxy. So that technique that I just walked you through identifies potential dwarf galaxies, right? These are overdensities that could plausibly occupy, stars that could plausibly occupy the same region on the sky, the same distance from us. So let me go back very quickly to the good question in the chat about why this group of green stars is so spread out. And that has to do with the fact that Segue 1 and similar dwarf galaxies that I'll talk to you about are really very close in cosmic terms, which spreads them out on the sky. So this image is probably about a degree squared. And the dwarf galaxies and ultra-faint dwarf galaxies typically occupy roughly several tens of arc minutes over densities. So in terms of physical size, these are actually quite small galaxies, but they're so close to us that they're kind of smeared out over the sky. Okay, good. So using this sort of algorithm, we can, in an automated way, search for these dwarf galaxies over much of the sky. But there's still something that is, probably bothering you, which is, well, how do we actually know that a clump of stars that might be at the same distance is actually part of the same gravitationally bound system? And so for this, like I alluded to earlier, we really need measurements of the electromagnetic spectra emitted by the stars, or spectroscopic measurements. And those measurements tell us, as I said, how quickly the stars in a certain group are moving. And we can use that to infer how much mass there is relative to the amount of light in a system. So that's a lot of words. Let me show you some pictures to illustrate this. We know that our Milky Way has a mass to light ratio of roughly 10, meaning that there's about 10 times more total mass in the Milky Way that dictates the dynamics of its stars relative to the amount of luminous matter. And as we go down in mass, so as we go down to the Magellanic Clouds and down to the classical satellite galaxies that I told you about, that mass to light ratio actually increases. So the classical satellites tend to have mass to light ratios of about 100. So those ultra-faint dwarfs that were discovered by SDSS occupy a really remarkable region on this plot. They have mass to light ratios as high as 1,000, or some have even higher mass to light ratios. And that makes them, as I said, the most dark matter dominated systems that we know about. And this is crucially what distinguishes them from other small groups of stars that don't have high mass to light ratios, or that don't have a lot of dark matter. So there are also, many groups of stars of similar size and luminosity as the ultra-faint dwarf galaxies, but that are not dark matter dominated. And those are typically referred to as globular clusters, and they occupy usually the inner regions of the Milky Way galaxy. So this is kind of the picture to keep in mind for how we know that ultra-faint dwarfs are really dark matter dominated and what their properties are. Okay, good. So now I want to come back with that framing to the discovery story and tell you about the Dark Energy Survey, which is a survey that came after Sloan finished taking data. In fact, the Dark Energy Survey mainly ran from 2015 to 2018 at that, well, with a camera mounted on the telescope that I showed you in the first slide in Chile. And this camera on the Dark Energy Survey was really very powerful. So just as a point of comparison, a typical camera on, for example, an iPhone takes images with about 12 million pixels each. The camera that was used to conduct the Sloan Digital Sky Survey was able to take images with about 120 megapixels each, so roughly 10 times more pixels per image than something you'd get on an iPhone. And the camera used to conduct the Dark Energy Survey, known as the Dark Energy Camera, increased again relative to Sloan by a factor of about 4 more pixels per image. So that's great. That's really helpful for getting a deep photometry that allows us to detect very faint stars. And another really compelling aspect of the Dark Energy Camera is that its field of view is very wide. So the combination of these two things, really deep imaging over a wide field of view, is really exactly what we need for detecting these faint dwarf galaxies. And the exciting thing about the Dark Energy Survey was that it really delivered on this promise to detect extremely faint systems. So in particular, in the roughly 3 years or maybe 5 years since it started taking data, around 2015, DES discovered about 20 new dwarf galaxies and a number of other modern photometric surveys added to the known count of Milky Way satellite galaxies. So at the end of Sloan, we knew of about 27 dwarf galaxies around the Milky Way, and today we know of about 60, with new ones being added really all the time. So there are a few things to note here. First, you'll see that not all of those new dwarf galaxies are filled in as confirmed dwarf galaxies yet. And what that means for the unfilled ones is that we know that they occupy a distinct clump at a certain distance, but we don't yet have the spectroscopic measurements that tell us for sure whether they're a dark matter dominated galaxy rather than just a cluster of stars. Another thing to notice is that this nice image here shows the footprint of the sky that DES surveyed, and it happens to be right next to the large and small Magellanic Clouds. And that's actually extremely interesting from the perspective of dark matter that I'll tell you about later, It turns out that DES discovered many faint dwarf galaxies right in the vicinity of the Large and Small Magellanic Clouds, which has implications for the dark matter structure that's underlying these objects. Okay, so with all this in mind, we now have this really beautiful view of the Milky Way that I'll show you. So this is from the Gaia telescope, which takes these really gorgeous images. This actually has billions of individual stars shown in the image. You can see the Large and Small Magellanic Clouds by eye. And now with these fantastic discoveries of dwarf galaxies, we've really filled in much of the sky, as I said, particularly around the Large and Small Magellanic Clouds, and discovered really tens of new extremely faint galaxies. So this is super exciting. And one kind of very compelling aspect of this is that these dwarf galaxies are very diverse. So we have systems like the Large Magellanic Cloud, which, as I said, is roughly a tenth of the mass of the Milky Way, and it's actively forming stars. It's sort of a typical galaxy in some respects, at least. Then down to the classical satellite galaxies like Sculptor, which are much less massive than the Magellanic Clouds, and typically stopped forming their stars a few billion years ago. All the way down to the ultra-faint dwarf galaxies like Segway 1 or its cousins here, like Pictoris 1 or Eridanus 2. And these galaxies are really tiny. They have as few, as I said, as 1,000 solar masses worth of stars or even less. And in fact, they stopped forming stars uniformly within the first few billion years of the universe. So they've really been kind of quiescent dead galaxies for a very long time. Okay, so that's kind of the setup for the dark matter part of my talk, but I guess I think I'll pause there and see if there are any questions before I go on.
Any evidence for accompanying black holes?
Yeah, black holes, it's a great question. In fact, I was asked this question during my preliminary thesis defense by one of the professors at Kaipak. So no, the short answer is no. And the longer answer is we think that there are probably black holes at the centers of these dwarf galaxies, but it's really, really hard to know where to look to find them. So because the black holes are really small, you need extremely high angular resolution over a very small part of the sky in order to find it, but you need to know where the center of the dwarf galaxy is. And like the image of Segway 1 that I showed you on a previous slide, it's very hard to know exactly where the center of these dwarfs are. So we think probably yes, but we don't know where to look, I think is the best way to put it.
Well, research has been done in the formation of these galaxies and how they form?
Yeah, absolutely. So the our understanding of basically the reason that they stopped forming their stars a very long time ago, and this kind of gets ahead of myself a little bit, but I'll hopefully come back and make this more clear, is that these galaxies live in very small clumps of dark matter, and those small clumps of dark matter make it hard to retain a lot of gas and form stars efficiently in the early universe. So a galaxy like the Milky Way will build up its mass over many billions of years, but these really small galaxies, once they start to be hit by photons from other galaxies that are forming all around them, are just kind of shut down. It's too much energy input in order to keep forming stars. I think that might be made more clear when I show you the evolution of the universe plot in a couple of slides. But it's certainly a very active field of research.
Is the distribution of your of these faint galaxies is the distribution surprising to you in any fashion? I mean, they seem not to be uniformly distributed, and I just sort of leave it at that. Is there some explanation for why, or something along those lines that you might want to talk about?
Yes, absolutely. So this will be addressed directly in the next part of the talk. Well, there's two things. First of all, it is surprising because it's not really a uniform distribution when you look at it, and in particular, there are more than you would expect right around the large and small Magellanic Clouds, relative to, say, if these galaxies were uniformly distributed over the sky. And we understand this directly as a direct consequence of the fact that these galaxies form in clumps of dark matter and fall into the Milky Way, accompanying these dark matter clumps. So I'll show you a movie that I hope answers the question directly, and I'll point out when I do. And I saw one more question in the chat that is really good about what percentage of the galaxies that exist in the universe do we think are ultrafaints. And so by number, we think that ultrafaints completely dominate the population of galaxies in the universe. These should be by far the most numerous galaxies. Of course, by mass, they don't, right? Because they're so small compared to galaxies like the Milky Way.
How many of these is there a possibility that they're leftover remnants of a larger galaxy that collided?
Yeah, so most of these ultrafaints look pretty pristine in it. Well, I shouldn't use that word because it's on this slide. They look pretty unaffected by other galaxies around them. In particular, we can often tell that they've interacted tidally with the Milky Way galaxy because they're falling into the Milky Way. But they don't appear to have been built up by many mergers. And those mergers would typically reignite star formation, and we'd be able to tell that the stars are younger than we actually observe. So they seem to form in very isolated environments and then fall into the Milky Way. There might be one more question in the chat. Okay, good. So let's go on to the next part of the talk and see exactly how these ultrafaints tell us about dark matter. And what I'll try to convince you is that these systems are really awesome laboratories with which to study dark matter. So just a little bit of background, since we'll be talking about dark matter. So we think, or I should say, we have a very large and compelling body of evidence that dark matter accounts for most of the mass in the universe. In particular, about 85% of all the matter in the universe is dark. It really only gravitates, for all we can tell. And the sort of normal matter that makes up, galaxies and planets and stars and you and me only accounts for about 15% of all there is in the universe. So to go into a little bit more detail about this, as far as the 15% of visible matter is concerned, we have a really exquisite understanding of the constituents of this visible sector. So this is known as the standard model of particle physics, and it tells us exactly, what particles compose and, what their masses are and what their charges are and so on. So these range from quarks that bind together through the strong nuclear force to form neutrons and protons, to light generations of particles like muons and neutrinos, to force-carrying particles like photons. So we know all of these very well, and we have a very, very exquisite model that describes all of their interactions and behavior. On the other hand, on the dark matter side, we have absolutely no idea what the particle nature of dark matter is. We have many guesses, but we have no story analogous to the standard model of particle physics that tells us the dark matter is a particle with mass X and charge Y and interaction Z. So the guesses we have are usually split into these sort of classes, and I'll talk about some of these classes of different types of dark matter more a little bit later. But suffice it to say that we really don't have a very clear understanding of what dark matter is at a microscopic level. At a macroscopic level, though, on large scales, cosmology tells us actually quite specific things about how much dark matter there is in the universe and also where it is. And the reason we know this is that dark matter really provides the backbone for the formation of structure in the universe. So this cartoon shows a sort of picture of the evolution of the universe, from its very earliest moments of inflation and the cosmic microwave background as it expands until today. And what you'll see in this picture is that a really rich set of structure builds up over time. So stars form in the early universe and coalesce into galaxies. Those galaxies merge and grow, and it's results in this rich, vast web of cosmic structure that we observe today. And without dark matter, this story would really not unfold. In particular, these cosmic structures that we see in this slide would never form. So let me show you a movie to make that hopefully more clear. So what these movies will show are two universes that my group simulates on supercomputers. And in particular, what's being shown is the buildup of dark matter. So the density of dark matter over time as the universe evolves. So lighter regions will evolve to higher dark matter density, and darker regions will stay with very little dark matter. So what we see is that the universe on the left, which has about as much dark matter as we think our universe has, grows into this rich web of cosmic structure that's actually very similar to what we observe when we look up at the sky, of course, in galaxies. Whereas the universe on the right, which has very little dark matter, has a very hard time growing any of that structure. So a galaxy like the Milky Way would never form in a universe without dark matter, and we would never be here to talk about dark matter in that kind of a universe. So let's focus this in a little bit on the Milky Way in particular, because I've told you that these faint galaxies are orbiting around the Milky Way. So what you're going to see in this slide is another simulation, but now of the formation of a dark matter system that is specifically chosen to resemble the Milky Way. So let me optimize the video. Hopefully that makes it play more smoothly. Okay, so what you're going to see in the center of the screen here is the kind of dark matter structure that builds up to form the Milky Way. And also what you'll see is another dark matter structure kind of building up its own mass and then falling into the Milky Way at late times, exactly analogous to how we think or how we've observed the Large Magellanic Cloud to be falling into the Milky Way today. So let's see, hopefully this plays smoothly. So if you keep your eye focused on the center of the screen, you'll see the Milky Way kind of growing in mass as the universe evolves. And then towards the end of the movie, the Large Magellanic Cloud will fall into the Milky Way on an orbit that, as I said, is chosen to resemble the orbit of the actual Large Magellanic Cloud that we see on the sky. And these simulations, I should say, are a lot of fun to work on. This is one that I actually ran and analyzed. And if you look at the output of one of these simulations at the end, after all the structure is formed, this is what you see. So there's a few things to break down here. There's a lot going on in this image. The first thing to notice is that the brighter regions in this image have higher densities of dark matter. So the white central region in the middle has the highest density, and these very dark regions at the outskirts have very little. Now, the Milky Way itself would live at the very center of this sort of picture. So the Milky Way, we believe, and we've measured, is enveloped in a really large, what we call halo of dark matter. So that's this kind of large egg-shaped structure surrounding the Milky Way. And the dark matter is most dense right at the center of the Milky Way, close to where we are, actually. Now, there's another thing to notice about this image, which is that, the distribution of dark matter within this dark matter halo that contains the Milky Way is not smooth, right? There are clumps. There's these little spheres here, here, here. These are what we refer to as dark matter subhalos. Subhalo because they are living within a larger dark matter halo. And the nice thing about these subhalos is that if they're large enough, they host their own galaxies. So this should start to remind you quite a bit of the picture that we sketched out at the beginning, right, with satellite galaxies falling into the Milky Way. We believe that these satellite galaxies are living in dark matter subhalos, and that these subhalos are what bring the satellite galaxies into the Milky Way. And so this is really the key. This is what makes these dwarf galaxies such great laboratories to study dark matter. In particular, these very small dark matter subhalos are pretty susceptible to any microscopic properties of the dark matter particle. And so because these small subhalos are very sensitive, we can work out, based on the distribution of satellite galaxies, kind of what sort of physics is governing the dark matter. So I'm going to make that more specific in the following slides. So we're going to walk through a few different types of behavior that the dark matter can have, and then how it affects those small subhalos and what the dwarf galaxy observations tell us about those properties. So let's look at one. The probably easiest one to understand is the velocity of the dark matter particle when it's produced in the early universe. So there's some, complicated particle physics that governs when and why and where dark matter is produced in the early universe. And we'd really like to know what that distribution of dark matter was at early times. Now, if dark matter moves quickly when it's produced, we refer to that sort of model as warm dark matter, warm just meaning that it has a high temperature. Whereas the kind of standard model of dark matter we have assumes that the dark matter is cold, or that it moves very slowly on these cosmological scales. So these are two simulations, again, of a halo that's similar to the one I showed you a couple slides ago. So roughly the amount of mass we think the Milky Way has. But you'll see that there's a difference between these two sides of the image. In particular, in the left-hand side, there are many small subhalos surrounding the Milky Way. But on the right-hand side, there aren't, right? There are many fewer subhalos in this model of dark matter that is warm. And so the reason for this is actually pretty straightforward to understand. If the dark matter particle moves quickly, then it is too energetic to become gravitationally bound into these small subhalos. And that prevents those really small subhalos from ever forming. And so the game that we play is actually pretty simple in a way. What we can do is count the number of these faint dwarf galaxies around the Milky Way and compare that to the number that would be predicted based on these kind of simulations. And so the idea is, if the dark matter is too warm, it could never form enough dwarf galaxies to be consistent with the observations that we have. So that's the idea. The dark matter can't move too quickly, otherwise it would never produce the population of ultra-faint dwarf galaxies that we've observed. And this informs specific theories of particle physics in which the dark matter is produced in this warm state. So for example, if the dark matter is an additional kind of neutrino, sometimes referred to as a sterile neutrino, it's produced moving very quickly. And this argument basically puts a pretty stringent constraint on that scenario, which is great. So moving on, I want to turn to the interactions that the dark matter particle can have beyond gravity. So again, these are two simulations, in fact, that our group ran of a Milky Way-like dark matter halo. Again, the brighter regions are denser in dark matter. The left-hand side is, again, the kind of standard case of cold, so slowly moving and non-interacting dark matter. Whereas the right-hand side is a model known as self-interacting dark matter. So what these self-interactions, you can think of them as is really just like a collision of two billiard balls, right? In this right-hand model, dark matter particles can bump into each other and exchange energy and momentum and then go on. These self-interactions tend to really mess up the structure of small subhalos. So if you focus on the large subhalo, which is chosen to resemble the Large Magellanic Cloud in the simulation, and you look right around it, in the cold standard dark matter case, there are many of these small dark matter subhalos right around the Large Magellanic Cloud, and those are exactly what was asked about earlier. Those would host those really faint dwarf galaxies that we see right around the Large Magellanic Cloud. But in the case with dark matter self-interactions, none of those subhalos end up surviving until today. Now, the reason is basically because the Large Magellanic Cloud is falling into the Milky Way really quickly. So the particles in these small halos run into basically a wall of other dark matter particles that they can scatter off of. And that process unbinds the subhalo and completely disrupts it. So this, again, allows us to use a counting argument of sorts to say that, well, dark matter can't interact too strongly with itself. Otherwise, we would not produce this overabundance of dwarf galaxies that we observe right around the Large Magellanic Cloud. And again, this informs specific theories that, in this case, theories that give additional structure to the dark matter sector. since those often contain or mediate self-interactions. Now, there's another sort of interaction the dark matter can have, and unfortunately, I can't go into too much detail on this just for time reasons, but this one is really close to my heart. It's something I worked on during my PhD. And that's to say that the dark matter also can't interact too strongly with normal matter for exactly the same argument that I gave before. And actually, this case is pretty analogous to that of the warm dark matter that I showed you. So if dark matter interacts very strongly with normal matter, then in the early universe, normal matter heats up dark matter and effectively makes it warm. And that means that, as before, this process can't happen too drastically. Otherwise, we would never form these dwarf galaxies. Okay, so one more example, just to really drive home the point. And this one I think is really quite cool. So let me walk you through this slide. So the standard assumption for cold dark matter is that it's a relatively massive particle. So, of the same order of mass of like a proton or something like that, maybe even more massive. Particles like that have quantum mechanical behavior that's confined to very small scales, right? We have to probe like, a proton at very high energies and look really inside of it to understand that it's really a quantum mechanical object. On the other hand, if we decrease the mass of the particle that makes up dark matter, then that quantum mechanical behavior ends up manifesting over larger and larger scales. And this is known as fuzzy dark matter. So if the mass of the dark matter particle is so small that its quantum mechanical behavior is actually like stretched out over cosmic scales, then we refer to it as fuzzy dark matter. And what this does is it actually suppresses, it inhibits the formation of these very small clumps of dark matter, essentially due to the uncertainty principle. You can't pack too much of a wave into a small space, otherwise it will destructively interfere with itself. So this argument then, the dwarf galaxies imply that the mass of the dark matter particle can't be too small. Otherwise, its quantum mechanical behavior would be too drastic on large scales and dwarf galaxies would never form. Okay, so I've come to another good stopping point. I'll see if there are questions there and then go on to the last part.
So are you ruling out axions, or what is your conclusion from this?
Good. So I was politically correct and didn't say anything to that regard. But since you asked, the sorts of, so just maybe for context, axions are a type of particle that have been hypothesized by particle physicists actually completely independently of the dark matter problem, and they are very interesting for particle physics reasons. The sort of axions that are super light that you can constrain this way are not the same thing as the axion that particle physicists have hypothesized. So let me say this another way. These constraints definitely rule out a large region of parameter space for dark matter models, but they're not ruling out the kind of favored axion that solves the particle physics problems. Those can still constitute dark matter that's quite cold.
Thanks for the clarification.
Yep.
So can you go back to the these things are relative measures, is it can't move too quickly, it can't act too strongly, and so forth. Is do these relative things actually provide any useful constraints on what the numerical values are going to be? And then to some extent, as I sort of see it, is part of what you're trying to do is to use these features to constrain the number of these satellite galaxies that you're seeing. But aren't the number of satellite galaxies that you're observing determined by how sensitive your criteria are for looking for them.
Yep, yep.
So you can essentially get any number you want in terms of numbers by changing. I mean, to some extent, is if the constraints for how you define whether you have one of these satellite galaxies or not can be determined by how you define things.
Yeah.
How sensitive you are is how do the models actually provide useful constraints in the end.
Yep, absolutely. So good. Let's see, multiple very good questions embedded in this larger question. So first, as far as the kind of relativeness of the measures, that's definitely correct, right? I mean, these are all, in other words, another way of saying this is these are all kind of like one-sided limits right now. Like the interaction strength, with itself can't be too large. But this is still, I think the compelling part about this is actually these are quite a few different properties of dark matter that I'm showing you here, and that actually rules out many different dimensions of the properties the dark matter can have. So just to contrast, this is really kind of a straw man example, but just to give a contrasting case, direct detection experiments for dark matter on Earth look for a very specific class of models, right? They look for dark matter that can interact strongly enough with the substance in the detector in order to cause, an observable scintillation of light. This is really the opposite, right? I think this is the opposite of looking under a sort of lamppost guided by specific models. And what we've seen is that the kind of size of the parameter space ruled out by these methods is actually very useful and informs, the kind of theories that are developed by particle physicists. And then following that, you're also absolutely right that the number of satellites that are detected is a function of the sensitivity of the surveys, right, that are searching for them. And this is really crucial to model. So in fact, this was probably a good 2 years of my PhD spent thinking about this part of the problem very carefully. And what we do is, in fact, mock up. So let me go back to the simulation picture just to make this more clear. So when we run this kind of simulation and then compare it to the data, we actually mock up exactly how sensitive each survey is. So we say, okay, we could be an observer living at this location in the Milky Way, and then we're observing this part of the sky with DES, and DES observes galaxies down to some luminosity threshold. And this is actually in the model, right? So that what we're comparing is the number of galaxies as they would be detected by surveys like DES and Sloan compared to the predictions of a particular dark matter model. So that's of crucial importance. And in fact, historically, there's been a lot of confusion about what dwarf galaxies may or may not tell us about dark matter because that part of the problem had not been treated carefully enough. Good. Okay. So now in the final part, this is not as long as the other two parts of my talk, but I want to show you that next generation of surveys will really be incredible for doing dwarf galaxy science. So let me start with this plot, which is actually related to the question that I just answered. So if we look at the distribution of dwarf galaxies that we have discovered to date in this space of luminosity versus distance, they would look something like this. So the Magellanic Clouds, very bright dwarf galaxies, we can detect those at fairly large distances. As we go to fainter galaxies, we can only see those relatively more nearby. So like the classical satellites, we can only see closer than the Magellanic Clouds. And similarly, ultra-faint dwarf galaxies, we can really only see those very close to the Milky Way. So in essence, there's a boundary, right, that current surveys can probe in this space, and we can't see any dwarf galaxies that are kind of living below this boundary. But the really exciting thing is that a few surveys, next generation surveys have looked at very small regions of the sky, but at really great depths. And every time we push past this boundary, we discover many new dwarf galaxies, as we would expect, because they dominate the universe by number. So in essence, what we can think is that next generation surveys effectively push this boundary down, and we'll be able to discover all of the dwarf galaxies lying in this region of the space. And luckily, there is a next generation survey that is going to do just this. So in particular, the Vera-Rubin Observatory will run the Legacy Survey of Space and Time, or LSST. And this survey is expected to find really all remaining dwarf galaxies around the Milky Way. So LSST is going to have a 3.2 gigapixel camera, and I didn't, the slide with the comparisons has gone by, but this is the largest digital camera ever built, right? That ever exists. And in fact, it's being built at SLAC just up the road in Menlo Park, which is awesome. So LSST, in addition to having the largest camera ever built, will observe the entire southern hemisphere, and will do so quite rapidly. So this is just incredible for dwarf galaxy science. And let me illustrate why. So here's a nice image from the Sloan Digital Sky Survey of a very pretty galaxy. And what I'm going to show you is the same region of the sky, but imaged by the Hypersea PrimeCam survey, which is one of those other surveys that I mentioned that has looked at a very small region of the sky, but has gone to quite great depths. And in fact, the depth of this image is close to what LSST will achieve. So we're going to have this kind of improvement, but not over 1 square degree, over the entire 20,000 square degree southern hemisphere. So this is really amazing. We're all extremely excited, and LSST is slated to start taking data within the next few years. So we expect, based on our current models and predictions, that the number of dwarf galaxies should easily more than double again in the LSST era. And in addition to discovering dwarf galaxies right around the Milky Way, LSST will also be able to find really dozens of ultra-faint dwarf galaxies outside of the Milky Way, which is also very exciting for kind of galaxy formation physics reasons. So these dwarf galaxy observations will be, for all of the reasons that I gave you in the previous part of the talk, extremely sensitive to dark matter properties. And combining one of the most exciting parts about dark matter science with LSST is that we'll be able to combine these dwarf galaxy observations with other cosmic probes of dark matter. So I want to just highlight 2 examples of these other sorts of dark matter probes, just to hopefully get you excited about why they're so cool. So one other way to look for these very small clumps of dark matter is using the technique known as strong gravitational lensing. So this is something that Einstein taught us about. So the basic idea is that mass or matter bends the path of light. So if we look at a distant, very bright astronomical object like a quasar, if its light passes through a massive enough clump of matter on its way to us, then the paths of those photons are bent. And in particular, the amount by which light is bent depends on how much matter is being passed through by that light. So in particular, we can use that kind of phenomenon to tell the difference between a model with many small clumps of dark matter, like a cold dark matter model, or one with fewer small clumps of dark matter, like a warm dark matter model on the bottom. And so I've actually worked on combining this technique with dwarf galaxy observations to kind of jointly understand what these 2 things are telling us about the distribution of these very small dark matter halos. And LSST is expected to discover something like 10,000, that's a very rough number, but of that order of magnitude, new strong gravitational lens systems. So combined with the new dwarf galaxy discoveries, this gives us really quite a bit of hope about the power of these observations. And one more example one more kind of illustration of the power of next generation dark matter constraints has to do with stellar streams around the Milky Way. So this image illustrates schematically what a stellar stream is. So as a dwarf galaxy falls into the Milky Way, if it passes too close to the center of the Milky Way, then it can be completely torn apart by the tidal forces imparted by the Milky Way's disk. And what that leaves behind is a long and kind of thin stream of stars on the sky, and these are known as stellar streams. Now, the nice thing about these streams is, as I said, they're very long and thin and actually kind of dynamically very cold, which means that if they're perturbed by any other clump of matter, that leaves a very kind of distinctive signature. So in particular, if a small dark matter subhalo passes through or near one of these streams, it generally leaves a kind of gap in the density of stars along the stream. And in fact, we've observed such a gap recently in one of the best measured streams around the Milky Way, known as GD1. So these are observations. These are actual stars in the GD1 stream observed using Gaia. And you can see that there are these gaps in the stream caused by, well, we don't know, but people are very excited because this might be caused by a dark matter subhalo. Okay, good. So wanted to come back here to wrap up to another really beautiful image of the night sky in Chile, and just paint on what we think the underlying dark matter structure is on this part of the sky, which I find quite beautiful. So these are the three main points. I'll probably leave them up, and super happy to keep answering your excellent questions.
I have a question. You keep showing terrestrial telescopes. Would it be better to have an outer space telescope? And is there, I'm looking at the list of outer space telescopes, and there's different, I guess, frequencies that they look for, ultraviolet, X-ray. You did have a picture of Hubble in one of your photos. You know, something
Yep.
like Kepler or TESS, which are way out there, I guess, and really focused on, you know, in whatever you want to call it, cataloging what's out there. I'm just wondering if you're able to piggyback on any of those projects.
Yeah, absolutely. So it depends a little bit on what the goal is, but definitely telescopes like James Webb, for example, will be really excellent at detecting these faint galaxies all the way to like very early times in the universe. Now, the trade-off is that, you know, it's hard to go deep over a large part of the sky with those types of telescopes compared to what we can do with LSST, which will get the whole southern hemisphere basically every few nights. So I guess that's part of the trade-off, is really depth versus sky coverage and like cadence. Of course, it's also very difficult, you know, there are many competing use cases for those space telescopes because they're useful for a large number of things, right? But certainly for observations like the strong lensing quasars, yeah, it has to be something like Hubble to get really precise data.
So something like TESS, which I think is going to spend like a month staring at each sector, and it's going to map the entire globe 360. But is that the wrong wavelength for what you guys would? I mean, could you use that data, for example, to look for?
Yeah, I think it would be difficult. I think TESS will do, yeah, as far as I know, TESS will do really amazing things for exoplanet science. But I think at those wavelengths, essentially, yeah, the photometry is not precise enough, right? Yeah.
Hi, I have a question. Are there assumptions about the composition of dwarf galaxies? I can imagine that dwarf galaxies may have varying compositions of stars versus dark matter versus gas versus, you know, whatever. I remember years and years ago, I was at a seminar and I asked the speaker, what's the smallest object that's ever manifested evidence of dark matter, and he showed a picture of a dwarf galaxy, as a matter of fact, And he said this particular galaxy shows no evidence of any dark matter at all, which I thought was interesting. So are there any assumptions about the relative composition of these dwarf galaxies and how that would change your ability to detect them?
Yeah. So let's see, there's a few things. The first thing to say is that the relative composition, if you like, or the mass to light ratio is a pretty strong function. It's strongly dependent on the luminosity of the galaxy. In particular, those ultra faint dwarf galaxies that I showed you are basically uniformly gas poor and metal poor. So these are really very ancient stellar systems that have just been hanging out apparently since the first few billion years of the universe. Now, as you go to slightly more massive galaxies like the Magellanic Clouds, those still can have a lot of gas and be actively forming stars. So that mass to light ratio, in fact, there's a lot of scatter is one way, is kind of how we like to say it. There's a lot of scatter in that quantity that makes it very hard to predict, like for a given dwarf galaxy, exactly how much dark matter it'll have. But on the whole, they're all consistent with being dominated by dark matter. In some cases, the measurements are not precise enough to say for sure whether the mass to light ratio is 1 or 1,000, and that's just because there are very few stars in those systems. And I think I should also mention, just because it's kind of confusing and it's in the news a lot, these kind of galaxies without dark matter that you might have heard about.
Yeah.
Those are much more massive dwarf galaxies than the sorts of systems that we're detecting around the Milky Way. I mean, they're much more distant, right? So they should be, because we're detecting them at like 20 to 40 megaparsecs. And in those cases, there appear to be other reasons that essentially deplete the dark matter, like tidal interactions with the galaxies they're orbiting. But they're a different kind of object, just to kind of flag that.
Well, maybe gravitational lensing would allow you to just weigh these galaxies without having to worry about their composition.
Yeah, that's one of the very promising things about, for example, the strong lensing technique that I showed you. It makes no assumptions, right, about the mass to light ratios in these systems, which is, both nice, but also, like, if you want to understand the mass to light ratios in these systems, then it's a little challenging, right? So again, it depends what side you're interested in, the astrophysics or the cosmology. So I see a few good questions in the chat too. So how can you distinguish between a globular cluster versus the nucleus of a dwarf galaxy? You can't unless you have spectroscopic measurements, right? Unless you know what the velocity dispersion of the stars is, then you really don't know. I mean, those systems look very similar in terms of their structural parameters and in terms of their composition, like their kind of metallicity and so on. James Webb, we touched on a bit. Yes, definitely. James Webb is going to be awesome for detecting high redshift faint galaxies. People are very excited about this. And I think it's supposed to start taking data also, hopefully within the next few years. We don't really know exactly when, but hopefully soon. Is there any reason to think that the region around the Milky Way may be different from other regions in the universe? So this is a really awesome question. And I want to go back to a slide that will illustrate this most clearly, probably here, but I'll have to go forward, which is fine. So yes, the region around the Milky Way is different than the rest of the universe. Let me go to a point in the movie that'll make that clear, maybe here. Oh no, I tried. Anyway, because a bunch of dark matter forms in the region right around the Milky Way, we know that region must have been denser than other regions in the early universe. So in that sense, yes, certainly, right? There must be a dark matter overdensity in the region around the Milky Way. So that's one point. Another point is that we know that the actual Milky Way has a very massive neighbor galaxy, right? Andromeda is not too far from us. And that configuration of two pretty massive galaxies right next to each other is pretty rare when you look at simulations. Furthermore, the Milky Way has a large Magellanic Cloud falling into it, which is another like pretty massive galaxy ending up very close to the Milky Way. So in that sense, again, yes, the Milky Way is kind of special and unique. So yes, those are the sorts of things that we have to think about when doing this modeling, because otherwise we would never be able to predict how many small subhalos, for example, should be found orbiting the Milky Way.
Is that group in the mid lower left there, is that supposed to represent the Virgo cluster?
Not on purpose, but it might in some sense. No, when running these kind of simulations, it's very difficult to really get more than the structure of the Milky Way itself. Even trying to find a pair of systems like a Milky Way Andromeda pair already means that you have to have quite a large volume simulation in order to find those rare events. So maybe it's a nice, I mean, it might be worth looking and seeing whether it has any properties similar to the Virgo cluster, but no, not on purpose at least.
What initial conditions do you assume for the distribution of dark matter? Can you elaborate on that a little bit?
Definitely. So the initial conditions are set, maybe it's the best slide. So the initial conditions are essentially set by our observations of the cosmic microwave background.
Right.
In particular, the cosmic microwave background tells us what the power spectrum of the dark matter is in the early universe, and that we can then essentially take a realization of that. It's a fancy way of saying, like, run that forward and simulate the evolution of the universe. Of course, we don't know exactly what kind of phases, so we don't know exactly like where in the sky dark matter was a little bit more dense or less dense, but these simulations are all done in a statistical sense, right? If we do enough of them, we expect that the kind of average to work out to the expected value. Great, I don't see any other questions. I'm sorry for running a little bit over, but I had a lot of fun answering questions. Yeah.
Just one more, because you had this slide where you're talking about all the different types of dark matter. I know those are the general theories of what states of dark matter could be, and it appears that most of your recent data is really all pointing closer to like the cold dark matter. Is that pretty much what your PhD thing sort of concluded, your work?
Yeah, so all of these observations that I've told you about, and in fact many other ones that don't have to do with dwarf galaxies, are all consistent with cold dark matter, or in other words, dark matter that is cold on the scales that we can currently observe. But the kind of tricky thing about cold dark matter is that cold dark matter is not actually a specific model, right? If we just say cold dark matter, well, that's not actually specifying what particle the dark matter is, what mass it has, what charge it has, what interactions it has, and so on. So I guess the way I think about it is cold dark matter is kind of a placeholder. It's the best we know right now, but at a microscopic level, dark matter has to be something different than cold, because any property you give it will make it not cold on some length scale.
Right, it's supposed to be just, but I mean, cold matter, dark matter is just a term for the set of parameters or the I think, as Ed was talking about, the generalization of the statistics that it would function in, right, as opposed to some of the other. But that's close. That's most of your observational data was pointing to that types of statistics, essentially.
Right. It's all consistent with cold dark matter, exactly. Right.
Well, it's pretty fascinating. It sounds like a great deal of study yet to be done.
Yes, it's a lot of fun though. Keeps us busy.
Yeah. So how many folks work in the group on this particular thesis?
Well, there are many people in KaiPAC working on the dark matter problem. Yeah, like I said, I've been working on the dwarf galaxy side of it for roughly the last 5 years. My advisor, Risa Wexler, and others in the Dark Energy Survey have been working on this problem too, like interfacing these simulations with observations. But there's a whole, rich set of work going on in our group that also doesn't, also has to do with dark matter, but not from the dwarf galaxy side. So using, for example, weak gravitational lensing and other cosmic surveys to map out the distribution of dark matter on large scales. So many people, there are about, I think, 20 people at any time in Risa's group. Yeah.
Some of the speculations about dark matter have had to do with wild space versus tame space, is one way I've heard it characterized. The notion that dark matter formed ahead of the type of matter with which we're familiar with, and then it kind of, if you'll pardon the colloquial expression, serves as kind of the scaffolding upon which the structure of the galactic groups is hung or based. Is there is dark matter thought to be, to the extent that it's understood, is it thought to be in process of formation still, or is it a fairly mature element of the universe as currently understood?
Yeah, that's an interesting question, actually, from the from the perspective of the observations I was telling you about, because they actually have something to say about that. So I had to work with there's a professor in India who works on theories of they're called late forming dark matter. And in those theories, what you try to do is essentially mess with the particle physics of dark matter in any way you can, so that you delay its formation as long as you can in the history of the universe. The interesting thing about that is if you delay the formation of dark matter, you generally make it too warm, because the longer you delay it, it has to transition from something else, and that something else is going to be warm. And so the dark matter inherits the warmth of that other component it's transitioning from. So our study, we actually used these satellite galaxy limits to place a constraint on that formation time. And what we found is that dark matter can't form any later than 1 week after the Big Bang. If it forms later than 1 week after the Big Bang, like if it forms 2 weeks after the Big Bang, then it's produced too warm to account for these observations.
So that kind of suggests that it is a mature element of the universe, that in order to be cold and not to in order to have the capability to form the subhalos and not to and for the structure to form the way you were describing, it would kind of need to be a mature component of the universe, not newly in formation and newly changing all the time.
Exactly. Yeah, exactly. That's right. And there's actually another side of that coin, which is, maybe dark matter has been around for a long time, but maybe it can decay, right? Just like, standard model particles can decay. But in fact, that messes up this structure on small scales too. If the dark matter can decay, well, then it gets a kick from decaying, right? By conservation of momentum. Yes. And that also kind of unbinds these small subhalos. And in fact, we're working on a paper, like as we speak, that places a constraint on the particle lifetime of dark matter using these arguments.
Okay, any other questions?
I got one kind of fun question. So you are fairly entrenched in this field of study, getting your PhD, and you're a fairly young guy. What do you want to see be accomplished within your lifetime?
Well, that's a good question.
Whether it's something you do or something that just is done based on what you think is possible.
Yeah, so I tend to be a little pessimistic by nature. I mean, I maybe before studying dark matter for 5 to 10 years, I would have said, well, let's discover the identity of the dark matter particle, right? I think that's going to be very hard, basically for the reason that I've said. Like, there are many, at a microscopic level, there are many different things dark matter can be. And so it seems unlikely to find exactly, look in the one direction that gives us the right answer. So that's kind of why I'm excited about these approaches that are sort of agnostic about the specific particle physics that governs dark matter and are trying to figure out just generic features, right, that it must satisfy. So I would love for there to be a detection of dark matter. If I could choose any one thing to happen, that would totally be it. But I guess the pragmatist in me is giving you reasons for why I think that might not be so likely. Yeah.
Seems to me the pessimism would come from finding out that dark energy is going to destroy it all.
Right. Yeah. So I try not to even touch dark energy because I'm sure I would end up feeling the same way after studying that for a long time.
Okay. Are there more questions for Ethan? If not, I invite you to stick with us, Ethan, as long as you have time. But if not, then maybe you could leave us. I guess we have the email for you or some way to pose a follow-up question if one comes up.
Oh yeah, absolutely. I think Marion has it, but I can also type my email in the chat. And definitely happy to talk.
That would be appreciated. Thank you very much. And it was an excellent talk, and we thank you very much for sharing it with us. And we certainly hope to see you again and to learn of your progress as time goes on.
Absolutely. Hopefully in person. Fingers crossed.
It would be our pleasure.